Um, Today I'll be discussing on high performance concrete. Now, first of all, we have to understand that what is the difference between high performance concrete and conventional concrete. Because conventional concrete means what we normally do every day. And for that, in IS 456, there is a provision for nominal mix, though that is the old one. Uh, with the change in cement quality, strength, and all these things, um, that will be changed. I think maybe the next version it will come. But those things are for day-to-day concrete. But what I want to emphasize on that I want tailor-made concrete. That means you want to get a concrete of a particular purpose, and if that purpose is known to us, for example, it should be fire resistant, or it should be acid resistant, for a which will be used in a floor shop, or it may be chloride resistant. So there may be several reasons why we may ask for tailor-made concrete, depending on the requirement of the industry. And nowadays, you see, this is not at all a problem because you have got several ingredients, cement, then you have got the pozzolanic materials like fly ash, GGPS, and you have got so many types of chemical admixtures, mineral admixtures. And there are many things which, if you add it to the concrete, then immediately the property of the fresh concrete and hardened concrete will change dramatically. And the change in the property of fresh concrete, that will really help you. Maybe you know that you heard about pump concrete. So there very high flow concrete. And there are problems. When you are pumping it to a particular level, what are the problems? So accordingly, keeping all these things in mind, you have to ultimately transport the concrete from the ground level to the a particular level, maybe 100 meter above that, and through pumping, and that concrete should be cohesive, and whatever concrete you have received at the ground level from your RMC plant, the similar quantity of concrete should reach there at the 100 meter level. So it is not that easy, and also it is not difficult. Only thing that you have to understand the physics behind it, or sometimes chemistry behind it, and accordingly, if you design it and make trial in the laboratory, you will get it. So let us start with this high performance concrete. Now you see, I was talking about different types of properties of high performance concrete. Normally, the design parameters are strength and workability. But through my previous discussion, we have understood that the durability is important. In aggressive environment, how it will behave. In acid environment, in sulfur environment, in chloride environment, how it will behave. That may be one of the requirements of the industry. And ductility. Ductility, as you all know that for earthquake resistant design, ductility is a very, very important aspect. And in this aspect, you have to remember one thing, that when you are trying to get high strength concrete, then you will slowly find that the concrete is becoming rigid. But that is not acceptable. We have to get normally those concretes can be used successfully for high-rise buildings, which people are using it. So these are the things we have to remember. Now you see that these are the aspects very important. Durability and permeability. Now you see, if some acid water or some sulfate, if it can penetrate through concrete, then what will happen? It will disturb the interface between the particles. That means the interface may be weaker, or it may make the interface weak. And as a result, what will happen? Strength will come down. So that is why normally what we observe that if we immerse a particular concrete cube, suppose, in acid for some time, maybe for 7 days, 10 days, and then if you try to get the strength, you will find less strength. That means due to acid attack, this strength has come down. Now, that's why the permeability. Permeability is very important because if this acid solution or sulfate solution, if it enters the concrete, then all these problems will crop up. And that's why I show you durability and permeability. That means if the permeability is less, then normally we will get highly durable concrete. Now, if it is less, that means is it zero? No. I am not saying about permeability zero. That means you can allow some amount of acid water or sulfate or whatever it is, you may allow, but only thing is that you have to also see whether the moisture movement is there or not. Pore to pore connection is there or not. So if you find that pore to pore connection is there, moisture movement is allowed to some extent, then nothing will happen. Otherwise, what will happen that if the moisture movement is not allowed properly, as a result, the water within the pore under high temperature, it will develop vapor, and due to that vapor pressure, the concrete may burst. There may be huge cracking. So it has happened several times that people are running after high strength concrete, but they are not considering moisture movement properly. So definitely permeability should be less, but some amount of moisture movement should be allowed to avoid the problem which I have already explained to you. Pumpability is also another problem, because you see why I am giving importance to these aspects, because if we understand the problem behind it, and then we can come up with solution. So pumpability means that you see, when you are pumping concrete from the ground level to the top level, then what you are pumping really? You are pumping stone chips, sand, cement, water, chemical mixtures, or some other particles you have added, say silica fumes or JGBs, whatever it is. So all these things you are pumping together to the top. So what you are expecting? You are expecting the level of cohesiveness, level of flow, whatever the concrete has got different property. All these things, whatever available at the ground level, same thing should be available at the top level, at the 100-meter level. Now question comes that it's it's a multi-phase material. And all these materials, stone chips, sand, cement, they have got different specificity. Automatically, and the particle sizes are different. Automatically, it is very difficult to take all these things together at the top level of same quality. It's difficult, but it is not impossible because people are using different types of viscosity modifying admixtures, and they are keeping the viscosity at a particular level, and which brings all the particles together, and it remains same level of cohesiveness, and then you are pumping to the top. Now, question is that when you are pumping, then obviously there is something with pump also. You have to pump at a particular pressure. Now, unless you do all these things, unless you use viscosity modified mixtures or the pumping pressure, all these things, then what will happen that at the top, maybe slurry will come out first, then sand will come out, then chip will come out, and whole thing will be a mess. You will not get the similar type of concrete at the top. So your total, objective is lost. So that's why your pumpability is so important nowadays. And most of the construction, high-rise buildings, you will find that the pumpability, they are accepting concrete from RMC plants, and they are pumping to the top. So it is a very common affair now. So you have to know. So then comes shrinkage. You know that concrete, it undergoes, some shrinking at the fresh state, plastic shrinkage. But it is not that, it is finished at the initial level. Maybe after 3 years, you will find there will be some, crack due to shrinkage. So even in the hardened stage, the concrete may sink. So you have to be very careful, because unless you control shrinkage, then it's a part of your durability. Because if there is shrinkage cracks, that means again there will be moisture ingress, again the reinforcement inside the concrete will be corroded, and as a result, your objective is destroyed, that you want a very good RCC structure. So that is one. Heat generation, whenever you are going for this mass concreting, huge concreting you are doing, then what happens? That there is a huge heat generation, and it should not be very high. First of all, people should be able to work there. Second thing, that more the heat, and that has got some negative effect on concrete. The negative effect of the hardened concrete during the hardened stage, the incipient flaw within the concrete may be widen, and it will be there, and as a result, you may get less strength in concrete. Now you see that this durability and permeability are the most readily attacked components. Cement paste, in the cement paste, these are the three culprits: tricalcium aluminate, calcium hydroxide, and alkali silica content. Because if the tricalcium aluminate is more, say 3A, and that is not at all good for concrete. But again, there must be some amount of tricalcium aluminate also, otherwise the reaction will not take place. So it should be within a permissible limit. That you have to check. Calcium hydroxide, you all know that when we are adding water to ordinary Portland cement, calcium hydroxide liquidates. And if that, uh, alkali reacts with some, aggregates, uh, and if this aggregate starts swelling, then that is not at all a good situation. Ultimately, concrete will crack. And alkali silica content, that is also important from that aspect, that that must be balanced. Otherwise, what will happen, that this alkali or something will create problems, right? Of course, silica is a good thing. Silica we have to manage nicely. So you see, these strategies to limit these negative occurrences, limiting total alkali, sodium and potassium in the cement, that you have to limit, and your testing of aggregate, because if it is reactive in alkali medium, then it's bad. And of course, the some kind of reactive silica in the form of fly ash or silica, a lot of reactive silica is there. You can add it to it, and in this way you can consume the alkali, which is the basic understanding while manufacturing Portland polymer cement or fly ash based polymer cement or Portland slag cement. Now you see, these are the few problems. That inadequate compaction resulting from segregation. If the particles are segregated or the compaction is not proper, you won't get the result which you are expecting. And similarly, the microcracks resulting from shrinkage, thermal success is not expected. Bleeding, you all know that if the bleeding is occurring, then that is not good for concrete. So if there are heaps of concrete and if the water is coming down from or coming out of this concrete, no, it is not good, because the water you have added for some purpose, and if it is coming out, the purpose is lost. And distribution of pores and viscosity, which I was saying, that is very, very important from moisture movement point of view, and that's why we have to check the microstructure also. Now you see, you have to avoid bleeding, blocking capillary channels, proper curing is required. Otherwise, whether the full hydration has taken place or not, that you are not sure. Addition of hydrophobic material. In many situations, you use, some kind of material which reduces the permeability of concrete, and that is required also, because otherwise, the aggressive agents will go inside the concrete, and ultimately it will destroy the interface of the particles. Now, pumpability, you see that it is you can equate to the resistance of bleeding. That means if the bleeding is more, it is difficult to pump to the top. Then the blockage, pumping failure, that's a big problem, right? And due to that, there will be segregates under pressure. Then the bleeding of water or segregation of water occurs due to gap graded aggregates. So we should not use gap graded aggregates for pump concrete. And the pumpability, common sense is that if all the sizes of particles are uniformly distributed or well distributed, then you should get better pumping concrete or pump concrete. Now you see this drying shrinkage and carbonation shrinkage. The carbonation shrinkage even takes place after a long time. It may continue for a long time. In industrial belt where a lot of gases are coming out and carbon dioxide is present there. In that case, in many situations you will find that there will be shrinkage due to carbonation. So whenever you are checking the health of a concrete, then you have to check whether the carbonation has taken place or not. If the carbonation has taken place and if there is some crack due to that, net result is that strength will come down. So that should be checked. Now you see that the shrinkage resisted by aggregates during compaction hardening cement paste when losses water. As you know it, shrinkage largely depends on three things: total amount of water in the original mix, elastic modulus of the coarse aggregate. Obviously, if you use some fine aggregate, that also you can include, and proportion of aggregates. Now, in many situations, we add gypsum to reduce shrinkage, but gypsum has got some negative effect also, especially on strength. Now, you see heat generation. Large parcel of concrete, I told you, generates huge heat. Now, obviously, the heat generation can be minimized, right? By using cement or where the lesser amount of tricalcium aluminate and tricalcium silicate. Because if you can, cement having lesser quantity of these two material, uh, you can expect less heat. Because you know from pigment chemistry how the tricalcium aluminate and tricalcium silicate is contributing to heat. Low heat cement produces less heat, that you all know. But only thing I must tell you that this low heat cement is not important to us. Important is that the composition of cement. Now, if you can control this tricalcium aluminate, tricalcium silicate, or if you can control the heat generation in some other way, that is the solution. So that one can even do it by using fly ash. So there are ways other than using low heat cement, which is available in the industry. One can control that heat generation. Fly ash is effective to tackle the problem of heat generation, just like it. And heat generation of blended cement, the sustainability lower peak temperature than OPC. PPC has got disadvantage. So we are thinking that way also. You see, whatever I have already told you, basically you have to get a workable concrete, cohesive concrete, and at the end of the day, there must be minimum force, but moisture movement should be allowed to some extent. So, keeping all these things in mind, if we say that, how we will be able to explain the others, that what exactly we want. That in one word, people are explaining rheology. And what is rheology? That I am coming to that. Now, you see that the segregation and breeding is controlling stability. The relative density is related to compactability. And this viscosity, cohesion, and internal friction. These three things are providing you mobility. Now, if you take all these three components together, that is rheology. Now, question comes that theoretically one can explain like that. But what exactly people are doing to understand the rheology? Before going into this self-compacting concrete and also subsequently, I'll be discussing rheology. I must tell you that now we want to discuss a type of concrete where no vibration is required. If you just press the concrete and due to its own self-weight, the concrete will be fully compacted. It will be compacted to your expected level. Now, if you take a core out of it, when it will harden, then you will find that it has reached to your expected level. Normally, within the concrete, 1 to 3% voids are there. But suppose you want to restrict it to 1% or even less than that. You can always check it. You can always check the permeability. So that's why, the most important thing is that we want to get a concrete which will be pumpable at any level, maybe 100 meters, 200 meters, and at the same time, what we expect that the concrete quality will not be compromised. Same thing, what we are getting in the ground level, same quality we should get at the top level. And due to that, if you want to get this, then obviously self-compacting concrete is the solution. And if you slowly go to the things, if the vibration is not required, obviously the reduction in sine manpower will be a faster construction. Pumpable, just it will go to the top and concrete will come out from the, some pipe, like a tap water. And easier pressing because it will go to different places automatically, improve durability, and there is no vibration, machine or anything, so noise level is zero. Now you see the composition of self-compacting concrete. Now cement, mineral admixture, water, chemical admixture, fine aggregate, coarse aggregate, all these things are there. Chemical admixtures, you can go for high range water reducers, super passages, viscosity modified admixtures. For mineral admixtures, IS, GGBs, limestone powder, or anything. Volcanic acid is not really available in India, but we can use other things also. We take urine. Now, let us now come to the rheological part of it. Rheology means, you are measuring the viscosity of concrete. That means whether the concrete is of highly viscous or less viscous, that you can decide that yes, I want this kind of concrete of this particular viscosity level. And you can measure it also. How? If you have got rheometer, then if you place your concrete in the rheometer and ultimately it is connected to a computer and it will give you some graphs and other things that I am not discussing in detail here, and you will get the viscosity level. So if it is within your expected level, fine. Otherwise, you have to revise the concrete ingredients, proportion, etc. to arrive at a particular viscosity level. Now, question comes that this rheological behavior, also includes thixotromy. Thixotromy means when you are making the concrete, at that level it has got some flow. But at the time is going, the flow will slowly come down because of setting. And after some time, the flow will be extremely less. Half an hour, 45 minutes less. So, if you understand, try to that, what is the setting profile, means with time, how the setting is coming down. From there, you can have an idea about thixotromy. And this is also another parameter which is required, which is very important because you have to complete everything within a time span. So thixotrope is very important. Now, you see, as you have already understood that this is just a concrete like water. It is not, no slump test is required because we are talking about liquid concrete almost. Now, naturally, when you will be able to declare that this is a self-compacting concrete, that is a very big question. So, there are around 10 tests. Out of 10 tests, I have mentioned only 4 tests here. Because these are the tests if you perform, then there is some limit, lower limit, higher limit, and if your value is coming within that higher limit and lower limit, then you can declare that yes, my concrete has passed through all these 4 tests, and it can be said that it's a self-compacting concrete. It may be recommended. Now these are the 10 tests. These are all 10 tests. So you can also go for 10 tests. And the purpose of the test, first to filling ability, then this is passing ability, segregation resistance. So all these things you will be able to understand through this test. Now you see, this is a particular slump flow test. So if you just lift this slump cone, the concrete will flow. So how much it is flowing? Is it 180 degree diameter or 200 millimeter or more than that? So that will give you an idea about the flow, and also when it will reach to its maximum diameter or within a particular time how much diameter it is reaching. So all these things are very important. So that way you can understand the flow. This is one test, V funnel test. V funnel test, is a funnel type things, and if you are pouring concrete, before that you can lock the bottom. You can lock the bottom, and then you pour the concrete, and then you remove the lock. Just remove this plate. What will happen? That all this concrete will come down and it will be collected in a container. Now, how much time it is taken to become empty? That is very important. That is important. That's why it's V panel test is defined this way. This is another thing. You see, you have got a cone, a slab cone, and these are the some round bars which are you can compare with your reinforcements. So previously concrete is flowing without reinforcement, the first test. But now suppose there is reinforcement and concrete wants to flow. Obviously reinforcement will provide some resistance to flow. So you will not get the same diameter which you got in the first test. Maybe some value, and that will give you a very clear idea about your concrete flowing through the reinforcements. Now you see, this is another test, U-box test. Now you see, if it is not concrete, water, what is happening? There is just a U-box and there is a separator here. So you fill in the concrete here, you fill some concrete here, right? And then you remove it. What will happen? This concrete will mix with this concrete. Even then, there will be difference in level. Even then, there is a difference in level. And that difference in level will indicate regarding your fresh properties of concrete, flow, or all these things. So, just compare, if it is not concrete, if it is water, just fill up with water some level, here's also something, water, and then you remove this, what will happen? This will be in the same level. If it is water, it will be at the same level. But for concrete, it cannot be at the same level, though it is almost like water. So, if it is less or if it is within the permissible limit, that means your objective of getting the self-compacting concrete is fulfilled. So, this is the way you have to finally say that I have performed this test and the values are within the maximum and minimum limits, and we can declare it as a self-compacting. With all these things you have to put in the report. So this is the table, acceptance criteria. Maximum value, minimum value. And so some people this. So I'm not going into detail of it, but these are very simple things. All these test setups are available in Haldia Institute of Technology, in the concrete technology lab. Our researchers are conducting research on self-compacted concrete regularly. So if somebody wants to learn or somebody wants to design a self-compacting concrete, I think HAT is the best place. They can come. Now this is a particular chart table where different types of mix are taken. Different types. Cement content, fly ash content, GGBS content, then cellular metakaolin. So like that, like so many things, sand, coarse segregate. So all are in terms of kg per meter cube of concrete. For 1 meter cube concrete, these are the quantity fixed. And accordingly, everything, then the super percentage, then BMA in percentage. So these are the uh, different types of concrete is considered and then tested, and finally you will get the result. This is another series. That was series A, which is series B, another set. Now you see, in most of the cases, in all those things, your strength is within 50 to 80. So you can easily imagine that is quite high. With our normal, kind of cement or that mixture, chemical mixture which you are using, with that we can achieve this. But only thing is that you have to be very careful that when you are using this cement or some other chemical mixtures or mineral mixtures, whatever it is, the compatibility is a big problem. If they are not compatible, then problem. Suppose company X has got a plus and company Y has got a cement. Maybe when you are using these two, they are not compatible, they are not giving you the expected result. But for a particular combination of chemical mixture and the cement from the two different companies, may be compatible. And so that's why there are many things regarding your selection of appropriate ingredients. And if you can do that, if you have that experience, and then the rest of the thing is very simple. So that's why this kind of concrete, anybody is handling, he should have good experience of the laboratory. Because first of all, you have to do it in the laboratory. If it is okay, then finally you can recommend it for the field. So it is not a theoretical thing. If for this, if somebody go for 10 trials, doesn't matter. But at the end, you will be able to achieve a self-compacting concrete between a strength of 50 to 80 MPa. So whatever I told you today, it is not the end of the concrete journey. There are many things inside it. Only rheology may be a different topic altogether, and we can discuss another day. So that's why I must always tell you that you have to understand the concrete behavior from the base level, and there are many things which are influencing the property of fresh concrete, and ultimately you are getting a concrete high strength concrete, high performance concrete, whatever you want. That means tailor-made concrete, means whatever your client wants. So that is nowadays it is possible. If you have got a good laboratory setup and if you are working in this area, you have good experience, you will be able to do that. And that is, always you will get in PhD. And that's why, finally I must say that one should never be complacent, but should ever alert for new problems, new solutions, and new opportunities. Because unless you keep your mind open, you may receive some kind of material from your client that where you need some new experience. You have to think in a new dimension. You have to go for several trials, but you will be able to get the solution. So I hope that you have understood self-compacting concrete. Uh, in future, we will be working on it. If required, you can always consult us. Thank you very much.